So in the last class, good afternoon, students. So in the last class, we were discussing the characteristic equations of four flip-flops, right? So and I discussed in the last class three characteristic equations, that is for D, SR, and JK. And T flip-flop I had given you as a homework, right? So I don't know how many of you have done, because I received only 2 or 3 responses. Okay, so let me start this class with the characteristic equation of T flip-flop, right? So we will discuss how to obtain the characteristic equations of T flip-flop. T stands for toggle. Okay, first we will write the truth table of T flip-flop, right? So then we will write the functional table, which has the previous state and normal inputs, and the next state, which acts as an output. Okay, so this is truth table of T flip-flop. I have T, Q, and Q bar, right? So and we are assuming the control input is always applied. Okay, so initially when T is equal to 0, and it remains in its previous state, and when T is equal to 1, it toggles, right? So toggles, I can write either Q bar or Q, which we call it as a toggling state, right? So if my previous state is 1 0, when I make T is equal to 1, it toggles. That means the present state will be equal to 0 1, right? So now to obtain the characteristic equation of T flip-flop, we require the functional table of T flip-flop. So functional table, what it contains? It contains the normal inputs, the previous output, and the next state output, right? So what are the normal inputs here? We have only one input, that is T, and what is the previous state output, which is Q, and the next state will act as an output, and which is represented as Q plus, right? So again we will assume the control input is always applied and the flip-flop is enabled, either on rising edge of the control input or on high level of the control input. Okay, since there are two inputs, one is T, one is Q, so what I can write, how many combinations we can write? So we can write 4 combinations: 0 0 0 1 1 0 and 1 1, right? So now we will write the next state depending on the values of T and Q, right? So you just refer the truth table of T flip-flop to fill out the last column here, right? So when T is equal to 0, it is going to remain in its previous state. So this is called the no change state. If my previous state is 1 0, and if I make T is equal to 0, it is going to remain in that state. If my previous state is 0 1, it is going to remain in that state only when T is equal to 0, right? So here the previous state is 0 when T is equal to 0 for first combination. That means it is going to remain in its previous state. The next state will also be equal to 0, right? Next, when T is equal to 0, Q is 1, previous state is 1, so it remains in its previous state, which is equal to 1, right? So when I make T is equal to 1, the flip-flop toggles. That means whatever previous state you have, the complement of that state you will get. That will be the next state of the flip-flop, right? So when T is equal to 1, for these two combinations, T is equal to 1 and previous state is 0. That means the flip-flop toggles. When I apply the next clock pulse, what happens? Q plus will become 1, right? Next state will be equal to 1, and if my previous state is 1, next state will become 0, right? So this functional table we are going to put in the form of K-map to obtain the characteristic equation. Okay, so now 0 1 0 1, this is two variable K-map because we have two inputs, T and Q, right? So what will be the equation? Fill those cells with these outputs 0 1 and 1 0, right? So I cannot group these two ones. I cannot put these two ones in one group, right? Because they are not adjacent, either logically adjacent nor physically adjacent. So I have to group them individually, right? So what will be the equation? What will be the equation? What is the term for this one? It is equal to T bar Q plus, and for this it is T Q bar. So which is equal to T XOR Q, right? So this is the characteristic equation of T flip-flop, which is XOR operation of T and Q. Okay. So this completes. This is your homework answer. Okay. So in next slide we will discuss the resistors. It is not RESI, it is REGI, where RESI is analog component and REGI resistors is a digital component. So what is a resistor? It is a collection of more than one flip-flop. That means we know that the flip-flop stores only one bit, either 0 or 1, right? If we want to store more number of bits, let us say if I want to store 4 ones in a digital component, right? So what I'll do, I'll use one flip-flop for each one, right? So one flip-flop we require for this one we require for this, third we require for third one, and the last one we require for last data, right? So now when I use one flip-flop, and if I combine them, and I can collectively call them as what? Register, right? So when I combine more than one number of flip-flops, then I can call collectively those flip-flops as registers, right? And registers we use to store multiple number of bits. Okay, and even these registers are available in the form of ICs, right? So you need not to connect the individual flip-flops to form a registers, right? So readily these registers are available in the form of integrated circuits, right? So next, what will so I hope you understood the basics of registers. So these registers are divided into two types. So one is based on the direction of data movement, based on the direction of data movement, and second one based on how the data is loaded and it is taken out from the registers. Okay, so these are the two categories of a register. One is based on the direction of data movement, right? So we call them as a shift registers. Okay, so here we are going to shift the data either in right direction or left direction, right? Next, based on how the data is loaded and it is taken out from the register, right? So before we shift any data towards right or towards left, we need to load those data into the flip-flops or registers, right? So in what manner we are loading the data in those registers, right? So even the registers are classified based on that. Okay, so now first we will see what are the shift registers. Later we will talk about how the data is loaded and how it will be shifted, right? So in next slide we will discuss what are the shift registers. Okay, so here we have two types of shift registers. One is the right shift registers and left shift registers. Okay, so we are going to form a shift register using a flip-flop, right? So I'll form 4-bit shift register. To be precise, we'll discuss 4-bit shift register in which we require 4 flip-flops, and the most simple among all 4 flip-flops is what? Which one? It is a D flip-flop, right? Whatever input you give, the same output you will get, right? Either 1, if you give input as 1, output will be equal to 1. If input is 0, output is equal to 1, right? So we will form, output is equal to 0. We will form a 4-bit shift register using 4 D flip-flops, right? So I will name the first D as D1, second D as D2, third D D3, fourth one D4, right? And we require a control signal, control input. All these control inputs are shorted and they are connected to a control input which we call it as a clock, right? So clock will so here I already told how clock looks. It is a square waveform, right? So either we are talking about this that is edge triggered flip-flop, or you can take this level triggered flip-flop. So here I will consider the edge triggered flip-flop, right? So this is the waveform of clock, right? Now, so what happens here when the data when the data is loaded in using first flip-flop, right? So here it is Q1, right? So now if D1 is equal to 0, if D1 is equal to 0, and if I apply this clock rising edge of this clock, right? So what happens? This particular flip-flop is enabled. Since the input data is equal to 0, the same output you will get. So Q1 is equal to 0. Let me draw the waveform of Q also. So I'll draw it Q1 initially, right? So when I am applying the first clock pulse, so Q1 is equal to 0. Q1, and what about Q2, Q3, Q4? They remain there in their previous states. They remain in their previous states because I am not applying anything to their D's, their corresponding D's. I am not applying anything, right? So here I am not applying anything to D2, D3 and D4. That means Q2, Q3 and Q4 will remain in their previous state, right? So now what I'll do, if I want to shift this data which is equal to 0 towards right, so what I have to do here, I have to connect the output of first flip-flop to input of second flip-flop. So now what happens, the data for second flip-flop will be the output of first flip-flop. The input for second flip-flop is the output of the first flip-flop, right? So where Q1 is connected to D2, that means once we connect Q1 to D2, what will be the data on D2? It will be equal to 0. So what happens here? So this 0, which was earlier, which was there in this first flip-flop, it has shifted to second flip-flop, right? And what will be stored here, that depends on the value of this D1, right? So if you keep it as equal to 0, then this flip-flop also remains in its previous state, which is equal to 0. If I make D1 is equal to 1, when the second clock pulse is applied, what happens? This 1 will be loaded here and this 0 will be shifted here, right? So I hope you understand. I hope you are following the things, right? So Q1 initially it was 0, right? And the Q2, Q3, Q4, they'll remain in their previous states, right? In their previous states, right? So now what happens when the second rising edge of the clock arrives, right? So what happens when Q1 is connected to D2, Q1, let us say D1 is equal to 1, D1 is equal to 1, what happens to Q1? Q1 will become 1 when during the next second clock pulse, okay? And output of Q1 is connected to D2. What was the previous state? You should not consider this Q1 value, right? So Q1 is now, it is changing because it suddenly it will not change. right? So here ideally I can say suddenly the value of Q1 changes, but practically if I connect and see, it will take very less amount of time. It will take very less amount of time to change. Either that time is either in nanoseconds, microseconds, but it will take certain propagation delay, right? So suddenly I cannot draw here Q2 is equal to 1, right? Because Q1 suddenly it will not change, it will take certain time. So in that case, the previous value of Q1 will act as input for the second flip-flop, right? So what happens to Q2? Q2 will remain 0. Q2 will remain 0 because the previous value of Q1 was 0, right? So Q1 has changed at this point, right? But it will not suddenly, I told, practically it will not suddenly change. It will take certain amount of time to change from Q0 to 1, right? So let us assume that time taken by the first flip-flop to change is this much, right? So in this duration, what is the value of Q1? Was 0, right? So at this point Q1 was 0, so this will act as the input for second flip-flop. That means Q2 will remain 0, right? So initially first flip-flop was storing 0, right? And the output of Q1 is connected to D2. So when I apply second clock pulse, what happens? This 0 will shift here, this 0 will shift into second flip-flop, and whatever input you connect here, that will be stored in the first flip-flop. So what will be the data in that case? It is equal to 1 0, right? So the previous 0 was shifted towards right, right? So now what I'll do, I'll finish this circuit, a 4-bit shift register, right? So output of previous flip-flop is connected to input of next flip-flop, right? So what happens here? Initially 0 was loaded and it was loaded in first flip-flop, right? And all the contents were 0, right? Initially, right? Now what happens? I'll apply the first clock pulse and we'll get 0 here, right? And remaining inputs will remain 0. Remaining outputs will remain 0. Next, what I'll do, I'll apply clock D1 is equal to 1. When I make D1 is equal to 1 and apply the next clock pulse, what happens? This 0 which was there in the previous flip-flop will shift to next flip-flop, and what is stored in the first flip-flop is 1, since D1 is connected to 1, right? So when I apply next third clock pulse, what happens now? If I make D1 is equal to again 0, right? What happens? This 0 will be loaded in first flip-flop. That means Q1 will become 0, right? And this 1, which was the previous state of the previous flip-flop, that will be loaded, that will be shifted towards right, and it will be loaded in second flip-flop, right? So what happens here? Q2 will become 1. Q2 will become 1, Q1 is becoming 0, right? And what is the value of Q3? Previous state of Q2 was 0. Q2 was 0 and it will be loaded in third flip-flop. That means Q3 is equal to 0, right? So now when the fourth clock pulse is applied and if I make D1 is equal to again 1, right? What happens? So this was the state, third state, 0, it was 0 0 here, and 0 1 0 0, right? So now see, 0, Q1 was 0, Q2 was high when the third clock pulse is applied, and Q3 was 0 and Q4 is 0, right? Q4 is 0, right? So when the fourth clock pulse is applied, so just make a correction here, okay? When the fourth clock pulse is applied, and if D1 is equal to 1, what will be stored in first flip-flop is equal to 1, right? And what happens to second flip-flop? 0 will shift towards right, right? So Q2 becomes 0, Q3 becomes 1, and Q4 will remain 0, right? So what will be the last state? It is equal to 1 4 zeros, right? So in the same manner we can also form left shift registers. In that case we are going to supply the input from right and we are going to check the output at